Hi, everyone. My name is Rahul Malik, and I'm an iOS developer on the Core Experience team at Pinterest. And what the Core Experience team does is we build tools, frameworks, and general abstractions to help everyone else in the iOS platform be more productive. So my talk today is called Writing Domain-Specific Languages in Swift. But before we get into that, I kind of want to talk about a challenge that my team particularly faces, and it's a common problem that a lot of people face, which is how do we move fast with quality? So generally, there's a lot of ways to move fast. You can hack a lot of things. You can do a lot of things to increase velocity. But over time, complexity generally introduces itself, and the quality aspect suffers. Now, you can add unit tests, you can add static analysis, but really, like an ideal scenario is that if the environment we were developing in would actually minimize our risk, if the development we were developing in would actually help us produce better code. And what I'm really talking about when I talk about this environment is domain-specific languages. This is a cat that moves fast. And a domain-specific language is a computer programming language of limited expressiveness focused on a particular domain. And the limited expressiveness is really the key of a domain-specific language, because the fact that it doesn't have to solve every problem as a general-purpose programming language means that it can focus on being really good at one thing. And you've probably interacted with a few DSLs in the past. If you've used a makefile, it's a DSL for build or shell commands. A pod file is a DSL for expressing third-party dependencies in CocoaPods. Or if you're using QuickCheck or SwiftCheck or Quick or whatever the newest Swift QuickCheck library is, you've used a property-based DSL for testing. But why should we write them? Now, DSLs are generally easy to use. They're limited in their syntax, and they're actually really easy to pick up. So if you create a DSL, generally someone else can use it really quickly. Because of the limited interface, you can generate type safety into it. You can actually provide enough constraints so that it's hard to misuse. And last but not least, it's declarative. So I don't have to convince this room declarative stuff is good. But really, like people that are using domain-specific languages, they just want to declare their intent, and they want to rely on the language to actually turn that intent into action. Not all languages, though, are good for writing domain-specific languages. I couldn't resist throwing this in my talk. This is from Robert. You'll be hearing him from later. So basically, he says C is basically a domain-specific language for writing unsafe code. So generally, if the language itself is a DSL for writing unsafe code, it's probably not one to write a DSL in. But functional languages are great for writing DSLs. And the reason is pretty much this, that the strong type system really helps you out. Higher order functions and lazy evaluation allow you to build composable and modular abstractions. And the fact is that, and a lot of them have pretty elegant syntax that allows you to actually feel like you're using a new language. And when I've done this at Pinterest, the sort of recipe I've come up with is pretty simple. First, we have to model or reify the problem statement. So generally, you have to think sort of abstract about what you're doing and figure out how to actually convert that into the type system. Then you have to build modular or composable abstractions, which are essentially transformations of that model to do what you want to do. It's basically turning that intent into action. And then last but not least, this is more of a tip, is work iteratively. Generally, you might be trying to model a problem that's actually quite big. It might actually have multiple subproblems, and DSLs are composable, so you can actually write multiple DSLs that interface with each other. And to illustrate this, I kind of want to talk about a couple stories at Pinterest. The first one is called PinCore. PinCore was an effort to modularize our application. Effectively, we had one giant iOS monolithic application, and we wanted to break it out into a series of modules and frameworks. Now, when you looked at one of these frameworks, we wanted to make sure that the file structure was actually the same throughout, so you had some level of consistency. And we took inspiration from the Swift Package Manager. And if you've ever used the Swift Package Manager, you might be familiar with this command, Swift Package init. Essentially, if you create a folder called My Library and you run Swift Package init inside of it, it'll create this directory structure where you have sources and tests and a bunch of Swift files, which essentially gives you an example unit test and something that sort of builds. And well, it builds. But we're trying to model our sort of we're saying we should write a script for this because we want to do something similar, but maybe we're going to diverge from Swift Package Manager at some point. So you can write scripts in Swift. So we're going to start off with creating some folders. We have a sources and test directory, and we're going to create them. And then inside the test directory, there's going to be like a framework name plus tests. And then After we have our whole folder structure, then we're going to start writing files. So we're going to be like grabbing like these like templates and evaluating them into strings and then writing them out to these like relative paths. And at first you're like, what's wrong with this? I can ship this. This is exactly what we wanted to do. But the problems are it's error prone. If you forgot to like create a certain folder before you wrote to that path, it might be undefined. It might work. It might not. You don't know. If someone was trying to refactor something in like in the area of the folders, you'd run up into other bugs. Outside of that, it's hard to follow. Generally, you're actually looking at this script, and it's not actually obvious what you're trying to build towards. And so right now it's only like 20 lines, so it's not that hard. But as this grows in complexity, it'll become more and more unmanageable, and it'll become that one file in your code base that no one wants to touch. And last but not least, it's imperative, which is like terrible. So it's actually hopping in and out of directories, evaluating templates, writing them out here. And so we want to get away from all that. So we want to talk about how you would fix this with DSLs. So our first step in the recipe is to model the problem. And I was going to talk to you about recursive enums, but you had an entire talk on that this morning. Effectively, by adding the indirect statement, the indirect keyword in front of the node case, or adding it in front of enum, you can generate recursive data structures, otherwise known as a algebraic data type. And with algebraic data types, we can actually now create a structure to represent the file hierarchy we were trying to create. So let's say we had this directory item enum. And it has two cases. One is a file and one is a folder. And the file just has a name and some contents. The folder has a name and it has a recursive callback to directory items. So it's basically an array of directory items. So it could be any mix of files and folders. Now, if we actually think about what we're trying to build, we can rewrite it like this, which is effectively, so you can see that the folder is called my library, and inside of it, the contents might have like a git ignore, then a sources directory, a test directory, and inside the test directory, there's another subdirectory. And it's quite readable. If you had never seen this file before, you actually can understand what it's trying to do. But the end result of this is just some enum type. It doesn't actually do anything. But then you actually say, okay, I can write functions to actually take advantage of this model. And like in this case, we have a root directory and we have an item that we're trying to render. So we're going to take the item and we're going to switch through it. And as long as you don't add a default case, as none of you ever should, the enums will actually make sure that your tests are exhaustive. So you're handling every case. So in this case, we write a file at a path. And then for a folder, we're going to make the folder and then go inside that folder and then evaluate its contents and then hop back out. And this simple function is maybe 10 or 12 lines, but now you actually have something that's testable and maintainable. But we don't have to stop there. Once you have a data structure like this, you can start to add other capabilities like ls. Like let's say you want to just test the output of a change. You want to just test if I'm making some change to our model, how would the file hierarchy actually be different? So you can actually write this command, which is just going to be another simple recursive function. Now, what we've done here is we've created a file hierarchy DSL that is otherwise known as a deep DSL, or a deeply embedded DSL. A deeply embedded DSL is one that results in a complex representation. So in this case, 1 plus 2 is equal to the expression of the sum operator and 1 and 2. Normally, you would expect 1 plus 2 to equal 3, but in this case, it's actually kind of describing, similar to the IO monad, what the output of this operation should be. And this is pretty great. Deep DSL allows you to provide, it allows you to understand how you got to that result. It allows you to provide further optimizations and transformations before actually sort of turning that intent into action. The second story I want to talk to you about is a project we open sourced about a month ago called Plank. So Plank is a code generator that takes JSON schemas and turns them into Objective-C models. It's a command line tool written in Swift, and so we thought it'd be fun to talk about code generation in Swift. And when you think about code generation, it's really a function that returns some array of strings. And you could imagine each index in that array being a different line in a file. So if we were trying to create, say, a generator to generate Fibonacci, we might wind up with something simple like this. If I is less than or equal to 2, return 1. else do the recursive Fibonacci call. But this is terrible. We could have messed up the syntax here. We're not only expressing that it's an if and else statement, we're also saying how if and else statements are rendered. And this is actually very fragile. And if we were trying to generate, say, 100 other methods and people were following the same patterns, it would quickly become unmaintainable. So we're going to say, we looked at enums last time, but this time we're going to talk about functions. And in this case, we're going to look at the structure of an if and else statement. An if statement, as everyone knows, is just some condition followed by an execution block. And the else statement is just another execution block that follows an if statement. Now, an if statement is really, so we could generate a function where it takes a condition that's a string, and then the body is really a code generator, which is type alias on the first slide as a function that returns an array of strings. And in turn, the if statement will return an array of strings. So in this case, and then we can take this exact same idea and apply it to else. And then we can take if and else and make if else. And if else is pretty much it's the composition of if and else, and we essentially return a closure that will actually take the else body. So in this case, if else has the same signature as if. So it's taking the if condition and the if body, but it returns a function that you will then pass another closure to. And to illustrate this is Fibonacci rewritten with if else. So now we're actually able to show that we have built something quite expressive, but we haven't said what the syntax of an if statement is. We've just declared that we want an if statement and that we want an else statement. You could have different language options and actually start to render different structures based on this. And this wouldn't really be possible without higher order functions. But since everyone in the room knows what those are, I'm going to skip over that. But higher order functions are really important for creating shallow DSLs. And this is what we expected the first time, right? So 1 plus 2 should equal 3. But the difference between a shallow and deep DSL is a shallow DSL is a fixed representation. So when we see the result of 3, we don't know that it was 1 plus 2 that got us there. We don't know if it was 4 minus 1 that got us there. We just know what the end result is. And in this case, code generation for what we did was a shallow DSL because it just returned an array of strings, but we don't know that it was if or if else that actually generated it. But for this talk, I wanted to also talk about stuff we didn't do at Pinterest. I wanted to come up with something special for you guys. So let's build something new. And the thing I want to talk about today is GraphQL. How many people in the room have heard of GraphQL or have played around with it? All right, cool. Nearly everyone. So I can skip over this slide pretty quickly. It's a query language for APIs. Most of you know that. And so instead of communicating with multiple endpoints for data, you're just communicating with a single endpoint. And I thought, I was looking for, I was going to set up my own GraphQL implementation for the demo or things like that. But I thought it'd be more fun to do something live with GitHub, something that everyone's familiar with. So let's say we wanted to actually get some information from GitHub. And the information we want to get is issues in a repository. So we might start with this repository query that takes an owner, which is Pinterest, and the name, which is Plank. And inside of that, we want to get a few fields. And then say we also want to display the avatar URL for the owner. And then we also want to add the first 10 issues. This is actually quite readable. And the great part is the API response is in the shape of the query that you actually sent it. So we could actually easily generate parsers for this JSON response as well. But GraphQL itself may be a little bit difficult to just throw into your project. And the reason is because it's an external DSL. And the idea behind an external DSL is it's its own programming language, basically. It has its own syntax. It requires its own parsers, its own tools. It's basically standalone. So it's going to be separate from Swift versus what we've been talking about this whole time, which is internal or embedded DSLs. Now, that brings us up to our problem, which is how can we actually write type-safe queries? How can we bring GraphQL into Swift? This is not a great idea, but but you could do something like this. You could basically say, okay, I tested it, I used curl, and I sent this, and I got a 200 response, and so I threw it into an array, and I concatenated it. And when you have a bunch of developers doing this, you quickly run into something that's not maintainable. You could have invalid syntax. You could forget to quote string arguments. You could be selecting fields and relationships that don't even exist. So what we want to start to do is we want to start to fix this. We want to bring GraphQL into Swift. So the first thing we got to do is we got to generate valid queries. And so to generate a valid query, we have to think about how we're going to model this problem. So the structure of a GraphQL query, in this case, I took a subset of our original query, which has the repository, an owner, and a name. So the owner and name are arguments, and then it has name, description, and then it has a query to another object type, which is user through owner, which it gets the avatar URL. So you can actually think about it as we can have objects with arguments, we can have objects without arguments, and at the leaf, if you think about this like a tree, they're all fields, or they're all scalar values. And once we know that, we can actually go back to enums, and we can create this node enum. And this node enum has two cases. One is scalar, which is just one of our fields, and the other one is an object, which is essentially a type where we're actually going to query for a set of fields in that type. And it has an optional set of arguments. And since the arguments cannot be just any type, we have a separate enum to make sure that we're type safe there. And then we just type alias to make this a little bit more succinct. And then we can start to actually take those raw strings and start to actually model them with our enum. And so now you can see that we have a repository label, we have our sets of arguments, and we have a first few fields. And then we can start to build on this by adding owner and avatar URL, and then we can add on our issues. And this is great. Like basically what we have here is we actually have a structure that represents a GraphQL query. And now we can take this structure and actually write a function to actually render the query string. So for a field, we're just going to print out the field name. For an object, it's going to be the object name, and then curly braces, and then your list of fields. And then for objects with arguments, it's the same thing, but with an arguments list. Now, the field arguments are also have their own function, and we're using the sort of exhaustive checking and switch statements to make sure that we're handling all of our cases here. So we just have string and integer, and this is just making sure that strings are quoted effectively. And this is great. Basically, we can write essentially a structure that will convert to a valid syntactical GraphQL query, but we have more problems. The problems we have are types now. We don't know that we're actually selecting fields, and like there's no guarantee that the fields we're selecting on repository or owner actually exist on repository or user. And so we need to actually figure out how to bridge this type system that exists in GraphQL into Swift. So then we go back to enums again. So in this enum, so there's only certain objects you can query from the root in GraphQL. So in our example, we had a repository. So we're gonna basically inline its arguments. So we have owner and name, and the last parameter is a field selection on a repository field. And a field selection is just a closure that returns something of type T, where T is a repository field. And then we can create enums that correspond to the various field names that are actually available and the relationships that are available on repository. And then we can also do the same thing for user and issue. And the cool thing now is when we had that node structure, it was great, but it was pretty verbose. So it was actually kind of a lot to look at. But now we actually get something really concise. We can actually utilize trailing closures to actually lift out that field selection out of the arguments list. And you can start to see the shape of the query forming. And the best part is that you can't ask for things like the avatar URL of a repository because it doesn't exist. You can't create relationships and query for relationships that don't exist. But now we have this structure that represents types and this structure that represents a GraphQL query. So we need to bridge them. And this is Swift. So the answer to everything is protocols. And so we have a very simple protocol called node renderer. It's just a render node function that returns a node. And then we can make query root conform to this protocol. And in this case, since we're doing exhaustive switching, we can handle the repository case, which is going to create a node object with the label repository. And then it's going to pass through the proper arguments and convert them to the input type enum that we declared in the first slide. And then we're going to have a list of fields. And the fields are going to be mapped over, and they're going to be rendered into nodes themselves. And the great thing is that by mapping over those nodes and sort of like having this recursive generation, we're going to guarantee that every enum in our type structure actually conforms to node renderer. And so now we're actually able to put the whole thing together. we're able to say that we have a type DSL that converts to this node DSL, which then can be rendered to a query string. So in this case, our query function is really just a field selection of query root, and it has an opening and curly brace, and inside we map over the fields, we turn them into nodes, then we take those nodes and we turn them into query strings, and then we just join them together. And rather than making you look through the last 74 slides, I would like to show you a demo. It's recording? OK, great. So over here, we can see that we have, I basically took that entire DSL we just talked about for GraphQL, and I dropped it into sources so we don't have to rewrite it again, as much as everyone loves live coding. But we actually can see sort of the base of our repository query. So, and we can actually use playgrounds to start evaluating this. So this query function that I told you takes the entire DSL and renders it to a query string. You can actually expand this and start to see the output here. And then I can start to actually add new fields, like description. Should update that. And then I can start to query other relationships, like owner. And in the owner, we want the avatar URL. And and rather than just showing you sort of string output, I whipped together a quick little live view because I thought it'd be fun to actually execute this against GitHub. And so there's our GraphQL query, and there's the response right next to it. And we can start to add other parameters or other parts to our query, like the issues. And for each issue, we want the title. And I have a compile error because I didn't say that we wanted the first issue. So the compiler is saving me. So we want the first 10 issues, which when this playground runs, we should see on the right side. And then we can drop it down to 1. And then we can actually lift this out, and we can create, say, I don't know, like a function like repo with issues. So we can actually template the whole thing. So we can actually say an owner is a string, and the name is a string. And then this returns a query root. And then, and the cool thing is now that it's templated, we can actually use this function instead of the whole inline query, and we can actually say we want a repository with issues, and for our host Kickstarter here, I want to say, I'm going to look at Kickstarter's issues, and bootstrapping fails because of native secrets. That wasn't meant as a call out. That was meant to show the power of parameterization of GraphQL queries. But you don't have to stop here. There's a lot more you could do with this. This is just the beginning. And I just want to say thanks. This is my first conference talk. So I'm happy to be here. Thanks, Chris and Brandon, for inviting me. And I hope you find time to write domain-specific languages on your own. Thank you. Sure. Anyone? Yes, fun story. So it is online. On my GitHub, if you go, I can try to post it after this, or you can just get me after. It's github.com/Rahul-Malik. And there's a writing DSLs repository there. Fun fact, I checked it in 2 days ago. And GitHub revoked my access token that I checked in with it. So I had to create a new access token like last night. Otherwise, the playground was going to be busted. Yes, there's definitely some. It's strange, right? Like, there's definitely times where I've had the compiler, just general type inference, give me errors like, oh, it can't resolve this type, this is ambiguous. But then when I add enough, sort of like when I actually say like, oh, it belongs to this enum, or I add like as some type, then it resolves itself. And then I can remove it again, and it's fine. So I actually don't really know. There's actually, when you have a non-deterministic compiler, it's actually quite difficult to understand how it should. Yes. Okay, will do. Any more? Yep. So this is actually a problem I thought about a lot about. Not with this DSL specifically, but when you think about GraphQL, you actually have this kind of interesting thing where a GraphQL query is going to return a set of types. And so really what you want to build is you actually want to still have repository, user, and issue. Like you want to have those as separate model types. But for every GraphQL query, you should generate a protocol that actually will constrain the types to actually everything you've queried for. So that way, if you only queried for the title of an issue, that would be available in your protocol, but say state wouldn't be. And that would actually provide some sort of level of type safety there. As far as like how to augment this DSL though, I would say in the original like node struct, I would say that we should probably figure out a way to bridge sort of type information into the scalar case, which will allow you to sort of like walk that same DSL and actually compare that against the JSON response. And you can use that for validation. You can use that for actually transforming into more complex types. But yeah. Thank you.